I have a couple of slides prepared. Like you see, it's very few. Then that will help me to introduce some theory so that you understand what we are doing. But we really want to do this hands-on. So we will be coding a solution, getting the data, trying to get the model to learn how to do sentiment classification and test the model on new data. So that's our plan for the next 40 minutes or so. Let's hope we can make it. After the meeting, I will share with you a link to the notebook that we will use throughout the session. So you don't need to worry about taking notes, like all of the codes that we will create. We will share it in the chat in the meeting. If there are any questions throughout the session, please go ahead and ask those questions. I feel it's sometimes good to answer questions as we go so that you don't get lost. If I go too quickly at some point, also let me know if I go too quickly. So let's start with the problem framing. So what are we trying to do with this text classification or sentiment classification? Let's use this exact two examples. So, and apologies for the quality of the scan. I could have improved it, but for now it should work. So let's say that we have a sentence. I liked this movie, and I put this sentence through the model. I want to get a prediction saying that this is a positive sentiment for, let's say, a movie review. On the other hand, if I write, I didn't like this movie, like it's pretty similar, right? There are a lot of similar words, like this movie, like it's very similar words, but the sentiment is different. So after I pass this review through the model, I should get an output that says this is a negative sentiment. So this is what we are trying to build. Now, because we are building a machine learning solution, we need to start with some data set, labeled data set that will give us examples of positive sentiment and negative sentiment. And we will use those examples to train a model, and then we will also test it. So where do we get such a data set? One place that actually we will use both for the modeling and for the data set is Hugging Face. And let me go there. I do this by intent that we kind of get this data and start preparing everything together, so that you can repeat a similar process, maybe on a different data set, maybe on a different problem in the future. So as you can see, I'm on this Hugging Face website, and let me search for sentiment classification. I have data sets here. Let me see all of the data sets that we have. I think I saw some notes. Let me check if we have anything in the chat. Is this no sound from me? Can you hear me?
Yes, we can hear you.
Okay, so Dixit, maybe this is on your end. Okay, so we have the data sets for sentiment classification. You can look up, maybe you can, as an exercise after this session, maybe you can take a different data set and build your own model. Actually, the one that I'm looking for is not here, but I know that there is a pretty famous data set called IMDb that contains movie reviews with positive and negative sentiment. So if you go to IMDb, you can see examples of text. I love sci-fi, I'm willing to put up with a lot, and there is a label, which is like, what's the sentiment of this review, negative or positive? Like, it looks like all of these are negative. Maybe a bit later on, maybe they are just sorted in an order of the labels. So we will use this data set, IMDb. Let me copy this, and then in order to train the model, ideally we need to have access to a GPU, the graphic processing unit, and to do that we will use Google Colab. So let me go to colab.research.google.com and create a new notebook that we will use to develop a solution. Okay, so this notebook is loading. Let me just call it Pi and AI sentiment. Okay, and what we want here is we want a notebook that would have access to GPU. So I will change runtime type. I will change the hardware accelerator to GPU, and I'll make it a high RAM runtime. Okay, and let me save this. Okay, so we want to work with IMDb dataset. So we need to import dataset library that will help us download this data, and we need to install it. We will also need transformers library from Hugging Face to build a model. So let's install both of these libraries. So we'll use transformers and we will use datasets, and let's just suppress the output. So this is installing, and once it installs, we want to load the IMDb dataset. So we'll need to use this function, load dataset, and we'll use it, IMDb equals load dataset, IMDb, and then we'll just take a look, what do we have here. Okay, so our dataset is loading. And as you can see, it takes a while to download, which means that probably this data set is quite big. Okay, so this tells me what we have just loaded, IMDb. It's a dataset dictionary which contains 3 subsets. One is called train, and this is data that we can use to train a model. It has 25,000 examples, and each of the examples has the text of the review and the label. We also have 25,000 examples for tests, and we also have an unsupervised data set which contains text but without labels. I think this label here is confusing. Now, we will not need this unsupervised data set. So let's just remove this. We will remove unsupervised. It can be used to train a model, but that will be a bit more complex. So we will not use this in our session today. Let's remove this. So now we have just train and test data sets. Okay, so this is better. Now, what we can do to accelerate training for now is maybe we do not need to use all of this data. Maybe let's just take a subset of this data. So we can do that with our dataset library in the following way. We will shuffle the data set. And as you have seen in the initial examples, like the data seems to be ordered. So let's just shuffle it so that we take a random subset of the data and select the first 1,000 examples for training. So that's how we take a subset of the data for training. We will just use 1,000 examples. That's not very much, but hopefully this will give us enough data to train a model. And if you want to build a better model, then you can take the whole training data set. And we'll just use 500 examples for test. Okay, we have quite a bit of chat. So let me just take a look. Okay. Yes, that notebook will be shared. Questions are welcome at any time, indeed. So let's do this, and let's take a look at our data again. Okay, so now we have just 1,000 examples in our training set and 500 examples in our test data set. So that should allow us to be much quicker. Let's take a look at one example specifically. So IMDb train, and let's take the first example from training. You can see the label is 1. Label 1 corresponds to a positive sentiment example, and then there is a text of the review. Let's maybe print that text to make it a bit easier to read. Okay, no, that didn't make it much easier to read. But anyways, you can see this is a pretty long review text of a movie that is, and you can spend some time to read it. Actually, for now, we will not need to read those texts. It's just enough to trust that the labels are done correctly. Let me quickly check the chat. Okay, can you follow what I'm talking? I try to address the question. Okay, so by the way, this session, in this session, I will assume that we'll go through some of the theory that will tell you like what we are really doing. For now, let's just assume that we have this text. We want to put this text into a model, and as an output, we want to understand, is this text positive or negative? So that's what we need for now. And in order to do that, we need a training data set. So what we're doing now is we're loading a training data set, which contains 1,000 labeled examples in our training set and 500 examples in our test set. Okay. Now, what we need to do next is we need to convert this text into numbers. And I assume you know a little bit of machine learning, but what we want to do is we want to put our text example into a model. A model is let's call it a mathematical function, and in order for that function to interpret this data, it needs to be converted into numbers. So how do we do that? How do we convert this text, which is a string with words and letters and characters? How do we convert this into numbers that the model can understand? So let's switch to the slide for a moment. And the way we convert text to numbers is by looking up the words in a vocabulary. And by the way, there are also different ways of doing that. But for our specific purpose and the approach that we will be using with a transformer model, that's a standard approach of doing this conversion. And to do that, we use a tokenizer. So what a tokenizer does is it splits our text. Like, I like this movie, it will split it into tokens. It adds some special tokens, like this initial S is a sequence start. It's a special token. This final /S is a sequence end, and again, it's a special token. So we add the special tokens, we split the text into I liked this movie and exclamation mark, and then we look up each token in the vocabulary to convert that into numbers that we call input IDs. So our text now is represented by a sequence of numbers 0, 100, 66, 40, 42, 1569, 328, and 2. So we achieved our goal of converting the text into numbers, and we will do this. And we will do the same for labels, where we will replace the negative label with value 0 and the positive label with value 1. So let's see how do we do this. Let me double check the chart. Okay. So what do we need to do? We need to have a tokenizer, and tokenizer is always connected with a model. And the reason this tokenizer is converted with a model is when we put these numbers into a model, we want to make sure that the same words are always represented by the same number. And the reason to do that is we will work with pre-trained models that already have some knowledge about text. They were pre-trained to try to understand text. So it's important that they always work with the same vocabulary, and we always do this in the same way. So each model has a vocabulary and a tokenizer that is associated with it. How do we pick a model to use? Again, we will use Hugging Face. So let me go into Hugging Face website, and there are many different models that we can choose from. A typical choice for English-based text classification would be Roberta, and Roberta comes in many different sizes. We want to do this training quickly here because we have a short amount of time for this session. So we'll use a small Roberta that is called Distill Roberta base. So we'll use this model. So let me copy this and go back to our notebook. We have this transformers library that we will use for our modeling. And from this library, we will take some classes. So we will have auto model for sequence classification. What we are doing here is a sequence classification task. Sequence is our text, right? It's a sequence of characters or words or input IDs. And we are classifying that into a positive or negative sentiment. We will also, okay, sure, let me check that.
Can you shoot?
Yeah, go ahead, please. Go ahead and ask the question.
Hi, thanks for the presentation. I had a question about how you choose the model. So there must be some well-known models, and I guess like there is some like known knowledge about which model works for which kind of data and the strengths and drawbacks of each model. And is there also like a verified accuracy of each model? Like where can I see those information?
Very good question. Very good question. And actually, there is a pretty new answer to your question that was just released, I think, today or yesterday. And let me quickly check. So I will show you this on Twitter. That's where I found the link. Let me go to Twitter to find the answer to your question. I'll go to Hugging Face profile. Hopefully I will find them here. Hugging Face, and I think they just tweeted a new feature that they have on their website. No, did they tweet it? Not yet, but so actually a person from Hugging Face tweeted this for sure. So let's check with Mervin. Okay. So this is the feature. And this is pretty new. So this was actually released yesterday. It's called tasks. So let's go to this link. You can use machine learning and Hugging Face library to solve different tasks. We are working on text classification. And as you can see here, there are like more than 2,600 models for text classification. So it's important to figure out which one to choose. So let's go and click on this link. And there are there is this part, models for text classification. Actually, it's like 15,000 models. So it's pretty low, a lot of models to choose from. And there are some models that are recommended here. Like for example, the Stillbird based on case fine-tuned SST, it says a robust model trained for sentiment analysis. So we can you can use this website with tasks to pick a model. you can browse the models. Sometimes, like the reason I choose Distill Roberta is because I know this is a good model. But if you don't have this prior knowledge from other cases, you can go here, you can browse the models, and you can check like text classification, languages, English, and then essentially go from here. Once you pick a model, if you click on this link, you will typically get a model card, which might contain some data. So if we like search for Distill Roberta, we should have some data on the model card, which will talk about what was the training data for that model, what was evaluation results. So so this Hugging Face hub with models is probably the good place to search, and it contains some information about the models, like accuracy and so on. But sometimes, like you can just ask people that have some experience with NLP, and they might be able to pick the right model or advise you which model to use. We'll use this to Roberta in this demo. Hopefully this was helpful.
Yeah, it clarified. Thank you.
Okay, good. And please keep asking questions. Okay, so what else do we need? We will need an auto tokenizer, and we'll also need a trainer to train a model. So let's import these classes, and we will use Distill Roberta as our model checkpoint. So let's do this, and then we need to load a tokenizer from this checkpoint. So I will use auto tokenizer from pre-trained and then model checkpoint. And I will do the same for our model. I will use an auto model for sequence classification from pre-trained, and again use this model checkpoint. It's important that both the model and the tokenizer are instantiated from the same checkpoint, because they need to be consistent. So let's load this. Okay, so our model and tokenizer are loaded. We can quickly check if the tokenizer is working as expected. So let's say we have this text: I liked this movie, and now we want to tokenize it, and let's see what comes out. Okay, so we have input IDs 0, 100, 66, 40, 42, and so on, and we also have attention mask. So let's quickly compare this with our slides. So indeed, like these are the numbers corresponding to these words. These are our input IDs. We also have this attention mask, and we will not go into the details of attention mask in this session. It's probably not so critical to understand. But one thing that will be quite important is to understand the concept of padding. This specific sequence, I like this movie. It has like 1, 2, 3, 4, 5, 6, 7 tokens. And it's just one example. As we train the model, we will have sequences that are maybe longer than that. But we need to always work with the same sequence size. And for that reason, we are adding padding. And this attention mask, one of the things it can help us is to differentiate which of the tokens are associated with the actual text and which of the tokens are associated with padding. So for now, please just assume that this is something that is handled for us by the tokenizer. You don't really need to worry about that at this stage, but hopefully this lets you at least a little bit understand what this attention mask is. Let me check the chat. I can see some people writing here. Okay, good. Okay, good. So let's go back to our notebook. So we can confirm that the tokenizer works. It can convert our text to input IDs. So now what we will need to do is we will need to write a function that will tokenize text and apply this function to our data set, because we want to convert all of these examples into tokens and input IDs. So this is how we do it. We define a function that we'll call tokenize. It will accept a batch of examples, and it will apply the tokenizer to the text field of those examples. We will also want to limit the length. Some of these reviews can be pretty long, so let's keep the max length of 512 tokens. This is already pretty big, and this is the maximum length for this model. So anyways, this specific model will not accept longer text. So let's limit this length of examples to 512. We will truncate the longer examples. So we'll always take the first 512 tokens. And if we have some shorter examples, we will pad it to 512. So this is what this padding does. So this is how we'll convert like this text. We will take we will change them into input IDs, into tokens. We'll take the first 512 tokens from each example. If we have a shorter example, then we will pad it. Okay, so we define this function, and now we need to apply it to our data set. So we'll do tokenized data set. And if you have a question, I can see we have a question. Please go ahead and ask.
Hi, would you prefer if I ask by typing, or is it okay that I ask you by?
Yeah, it's okay if you ask over the mic. That's perfectly fine.
Oh, okay, thanks. So I was wondering if this model that we are using now can also return the score instead of just label, like what percentage of positivity, for example.
Very good question. Yes, yes. With the model, we'll return the score. So we'll go here and talk about these predictions. Like what the score will be here. So I'll get to this. Thanks for the question. We're very close. We're very close. So we have now applied this tokenization function to our data set. So let's take a look at how it looks now. What are the features? So now the features are text label and also input IDs and attention mask. So we have now these numbers that we need to use to train a model. There's one more thing that we might need, which is a metric that will help us see how the model is performing as we train it. As a metric, we will use accuracy. This data set is a pretty balanced data set, so accuracy should be an easy and a good metric. And we will use this dataset library to load the metric. And let me just write this function and then explain what we're doing. So we'll load metric accuracy, and we need to define a compute metric function. For this, we'll need NumPy and NP and define compute metrics. I'll explain this in a second. Okay, so what we're doing here is we have defined a function that will compute metrics for our predictions, and we'll apply the predictions on this test or validation data set. Every time we check these metrics, we will run predictions for all 500 examples we have in our validation data set, and the predictions will be will always have two values, and there will be a value associated with class 0, which is a negative sentiment, and there will be a value associated with class 1, which is positive sentiment. And in order to calculate accuracy, we need to understand whether the model believes this is a positive or negative sentiment, and we will just pick the value with the higher confidence score. So in this case, like 61%, like 0.61 is bigger than 0.39, so the prediction of the model will be class 0. And this is what this argmax is doing. It's picking the class with the highest confidence from the predictions of the model, and then we calculate accuracy with this metric that we have just loaded. So let's save this function, and now we are almost ready to start training. So in order to train, we'll use this trainer class that we have imported from Hugging Face library. And this training class, it requires us to define the model. We already instantiated this model. It requires us to use some training arguments. We have not defined them yet, but we'll do so in a moment. We need to provide the trained data set. And this is our tokenized data set and the trained subset of it. And we also need test, no, actually not test, but evaluation data set. And this is again our tokenized data set, but now this is the test part of it. And then we also want to provide our compute metrics function that we have just defined. Okay, so we have everything except for the training arguments. Now, what are the training arguments? This is a set of hyperparameters which tells our trainer on how we want to train the model. And we need, in order to define these arguments, we'll again need to import a training arguments class from Hugging Face. So let's do this. From transformers, import training arguments, and let's define these args. We need to provide the folder where we wanted to store results, and let's just make it a temporary folder. And then we will want to define evaluation strategy. So we want to evaluate the model after every epoch. So let's write this down, and let's define the learning rate. Let's say the learning rate will be 5e to the power of -5. What else? Let's just train it for one epoch for now, because we want this to run quickly. And you can train it for longer. Maybe you can experiment with different learning rates. And because we want it to be quick, then let's also just run this in half precision with FD16 equals true. So we have now defined like a very small subset of training arguments. And let's instantiate the trainer with those arguments, with our model and with our data sets and with our compute metrics function. And once we do that, we'll ask the model to train. And this will be a good time to check if there are any questions. And I don't see any questions in the chat.
There's a question.
So let's see the model. Ah, there is a question in the chat. Okay. Before tokenization, if we remove the stop words, wouldn't that speed up the computation? Theoretically, yes. If we remove some words, then the text will be shorter, so the computation will be faster. However, let's consider the following scenario. Let's say I have a text. Let's say my text is I do like this movie, right? And then this is like a positive sentiment, right? But there might be another text which is I do not like this movie, and this should be negative. And guess what? Not is a stop word. So if we remove a stop word, which is not in this case, then we totally lose the meaning of the sentence. So for transformers, for the library and for the model that we're using, actually it is not recommended to remove stop words. How do we know the best learning rate to choose? From experience. And typically, like anything like in the range of 2e-5 to 5e-5 is a good default choice for transformer models for NLP. But you can experiment with different values. Okay, good questions. So let me just mark it as a comment, and I will say do not remove stop words. And this is an example to illustrate why this should not be done. Besides accuracy, do we use any other metrics? We can, yeah, good question. We can use any metric we want. You can use F1, recall, precision, other metrics. Like for simplification, let's just use accuracy here. As you can see, after one epoch, this model trained to the accuracy of around 86, 87%, which is probably okay. Now, what we want to do now is to test this model with some new examples. And let's create some examples. So let's create a test review. And this will be this movie is good. And now we want to apply tokenization to this example. So let's just write this example equals tokenizer test review. And let's check this example. So now you can see that this text was converted into input IDs and attention mask. Now, because we are just using one example for testing, now we don't need to worry about padding. So we can just take it with this length. And now we want to predict what our model thinks about this review. So let's create a prediction with our trainer. Our trainer still remembers the model that we trained, and we can use it to predict our example. And let's print our test review, and let's create let's now convert our actually let's take a look what the prediction is. So you can see that this, okay, so it's around the prediction. It says this movie is good, and it returns a prediction output with these two numbers, -2.375 and 0.082. So if we go back to the slides, as we trained the model and we created we had some bunch of labeled text. We tokenized this text to have input IDs and attention mask. We put this into the model. For every example, we got a prediction, which is a set of two numbers. One is the confidence corresponding to class 0, and the second one is the class 0, which is negative, and the second number corresponds with class 1, which is positive. And as we train the model, based on these predictions, we calculate the loss, which is how good the prediction is, and we use that loss to improve the model through back propagation. In inference, which is what we're doing now, we just take the text we get the input IDs and the attention mask. We run this through the model, and again, we get two numbers corresponding to the two classes, so class 0 and class 1. Because we have two classes, we can just take the number that is higher as the prediction of our model, or the index of the class with a higher prediction. What we're getting here in this prediction output is actually row logits, which we should take, if we wanted to convert this into probability, we would ideally run this through softmax, but actually this is not needed at this stage because we have just two classes. So we'll take the bigger number as the model prediction. So let me just complete this, and then I'll go into the questions. So how do we convert from this prediction to like a positive or negative? Let's take the argmax again from this field here, which is the prediction. So we'll take the predictions. We'll take the first element of those predictions because we just have one single example. But so this will be the element 0, and then we'll take argmax as the class that has the bigger value here. And then our labels are negative, which is the label 0, and positive, which is the label 1. And our prediction will be, well, actually, and we will now want to print our prediction. So print prediction, and our prediction is gonna be, let me just explain this in a moment. Okay, so what we are doing is we're taking the class with a higher value in this array, which is like in this case, the class 1 is has the higher value, and our labels are also in this order. So this is 0 and 1. So we're taking passing the 1 here, and this picks up this value of positive in our prediction. So this is how we go from this two numbers into actual text of the prediction. So let's check if this works. And this movie is good. The prediction is positive. Let's just quickly test like the stop word that we might have removed, which is this movie is not good. So let's run this again, and let's run again the prediction. And now the prediction is negative. So this stop word was pretty important, and the model picked up the meaning of that negation here. It went from a positive sentiment to a negative sentiment. Okay, let me check the questions now. Okay, we talked about metrics. We can use different metrics, but accuracy for this specific data set, accuracy seems to be a good metric. In NLP world, is there any rule of thumb like accuracy or any other performance metric above a certain percent is good enough? I would say the metric like this, I don't think there is a general rule. I would say there might be some values that are that might be applicable to specific data sets or to specific business problems. So if we are working with a data set like IMDb, there have been quite a lot of models trained on IMDb, and maybe we can even like Google, like let me quickly go from here. We can let me quickly Google IMDb accuracy benchmark. Okay, so you can see that actually sentiment analysis on IMDb is like has a benchmark here on papers with code. So it seems like the #1 rank is it has 97% accuracy. Our accuracy, which is let's go back. go back to our notebook. No, it's not here. So our accuracy is on the validation set is 87%, but we just trained it for like 30 seconds. And we only used like 1,000 examples from the training set. And we used a pretty small model. So I think it's pretty good with that regard. But again, IMDb is a data set that has this benchmark, so we can use it. If you are applying these models in a real business case, then the business case determines like what is your desired accuracy. If you do something maybe for internal reporting purposes, maybe 90% is good enough. If you are using the output of an NLP model maybe to make a diagnosis for a patient, then probably you're targeting a much higher target accuracy, like 99.999 or whatever. So it's always problem specific, this accuracy. Accuracy can be misleading sometimes, and we can use other methods to verify the same. Please correct me if I'm wrong. Yes, that's correct. That's correct. Accuracy typically is misleading if we have data set that is not balanced. We can check like this data set. I think it is balanced, so then accuracy should be good enough. But let's quickly check it. So we have this tokenized data set, test, and we want to no, this did not work. Okay, so as you can see, it's a balanced data set. So roughly half of the examples are positive and half of the examples are negative, which means like accuracy should be reflecting good performance. Also in this benchmark, they are using accuracy. Accuracy is a good metric for this specific data set. If this data set was imbalanced, I'll give you let's say that there is maybe just five out of 500 examples that are positive, then by always predicting negative, you would get super high accuracy. So accuracy is not a good metric if your data set is not balanced. But in this case, it should be good enough. Breyer discrimination. I'm not familiar with Breyer. I would I would normally use F1 score if accuracy was not good, but I'll check it out. Maybe Breyer seems to be interesting as well. Okay. Then what balancing method do you usually try? That's a good question. If the data set is imbalanced, then sometimes just training it maybe longer is still good. Sometimes you can use like oversampling maybe of this low class, and you can train the model longer with this class that is out of balance. You can maybe change your loss function and put more weight on the examples that are rare in the data set. So, but that's probably a bit more advanced topic. So it would be kind of go beyond the scope of what we can achieve today. What are some ways to improve the model? Maybe you can tell me, guys, like what would you want? What would you do in the next stage to try to improve this model? Any ideas? You can put them into the chat, or you can unmute yourself and say in the meeting. How would you go about improving the model? Increase the number of epochs. Yep, that's a good idea. I think that should help. In general, you can play with these hyperparameters that we defined here. So you can have more epochs. You can change the learning rate. cross-validation. So I guess cross-validation in the meaning that you train multiple models on different splits of the data and then ensemble these models. And then that is likely to help as well. Increased training size, definitely. So as you remember, we just took a very, very small subset of the data. So if we train on all of the data, the performance is likely to be better. You can also find ways of using this unsupervised data set, maybe with pseudo labeling, maybe with like pre-training the model. Try multiple pre-trained models. Yep. So you can also check other models in the Hugging Face Hub. You can use also other libraries like maybe ULMFit or others or FastAI. So yep. So very good ideas. Yes, you can see many different ideas in the chat. All of them are definitely good.
Yeah, you mentioned that we can utilize the unsupervised part of the data sets. How can we do that?
Yeah. So so one way would be to use this unsupervised data set for further pre-training the model. The model is pre-trained. The model that we use, this Phil Roberta, is pre-trained on a Phil mask task. Let me see if we have it. If we have it here. So if we go to this task, like there is this Phil mask task, where the model gets examples of sentences with some words randomly masked, and it is trained to predict the value of that word. That's how we are pre-training the models, and we're pre-training this on pretty big data sets like data crawled from the web or the whole Wikipedia, and we can use this unsupervised data from IMDb to maybe use this pre-trained task to improve the model for this specific domain, and then train it with the labeled data. Or maybe we can do like build a simple model, apply that model on this unsupervised data set, create these artificial labels that we call pseudo labels, and then train again with the pseudo labels. Sometimes this helps as well to improve performance. Okay, and this is actually the end of the session. We successfully trained a model that achieves like 87% accuracy on our validation set. We've done it pretty quickly. We can now apply this model on a random text. We can create something, like maybe let's create something more nuanced. Let's try to create an adversarial case that will potentially fool our model. So I hate broccoli, but this movie was actually not bad. Let's see if we can fool the model with this test review. Prediction negative. Yeah, you can see this I hate broccoli actually fooled the model. So it's kind of an adversarial example, and you can try to build a model that will still work with these adversarial examples, but you also need to take into account that sometimes it's pretty easy to fool the models, and there are cases where they are not working that well. Okay, one more question. With the availability of so many pre-trained models, where is the development and research in NLP headed towards? I'm not sure if I'm qualified to answer because I'm not an NLP researcher, but from what I've seen, one direction is actually trying to solve for this type of adversarial examples. I think this is an unsolved element of the NLP landscape. How do you get the model to actually understand? Like for a person, this is pretty straightforward, right? I hate broccoli, but well, actually this movie was not bad. If we can get our models to correctly predict for this type of adversarial examples, then that would be pretty good. I don't think we're there. Another direction is explainability, right? So how does the model make this particular decision? For now, this is like one big black box with a set of layers and neurons that we don't really understand how the model is making those decisions. And there are many cases where explainability is important. So that will be another direction. And then there is a whole trend of kind of training bigger models that can better understand text, and at the same time trying to decrease the size of the model so that we can run them more efficiently at scale. So that would be maybe some of the directions that I personally am excited about. Could you also try with this movie? Was actually not bad. Yeah, let's try this. This movie was actually not bad. Let's try. Okay, this is still negative. Oh, actually, I would expand this to be to work better. Was actually not bad. Yeah, so as you can see, but again, this model was trained for 30 seconds, so we can get it better. Now, before we finish, let me just make sure that I can share this with all of you. So let me save this and let me see if I can share. How do I share? How do I have sharing? Share. Okay, let me make it available and change to anyone with the link. Okay, anyone with the link can view, and I will copy this link and I will share it with everyone. So now you can access this notebook and play with it and try to build. So my challenge to you is build a model that will correctly predict this example. That will be pretty neat. And if you want to get in touch after the session, you can find me on Twitter. I think that's the best way to contact me. It's let me go to my profile. I'll ping you my link. You can connect with me on Twitter and ask questions there. Okay. Any final questions? I think we're at the end of the time that we have scheduled.
Wow. Thank you very, very, very much for this impactful and eye-opening session. I believe every one of us has learned one or two things today. We'll be closing with this word. We all have opportunity to push the limit of possibilities. We can always improve what we are learning and also create chance for others to learn from us. Thank you very much to you all for being here. Thanks to Mr. Darek for being here too.
Thanks everyone. Thank you for the invitation. I appreciate it, and thanks for listening. And good luck with your machine learning journey.